the platform is yours.
Thank you very much. I hope you can see my... Whoops, I'm muted.
Can you unmute yourself and activate your camera, please?
Sorry about that. Yeah, I forgot to unmute myself. Yeah.
You can
thank you very much. I hope you can see the screen now. And am I perhaps blocking? Okay. So what you're seeing here is a spherical pneumatic liquid crystal shell. Has just, or at least in the big... Let me see. It's supposed to be... Zoom is taking over, unfortunately. There we go. It has originally fully tangential alignment, and then we add liposomes to the outer phase. It's in water. I'll show you in a moment what a liquid crystal shell is. But the point is that what you see here are just the two first small islands that show that a phase separation in 2D is taking place. And as time goes by and we add more liposomes, more and more lipids are added, and you see that more islands are born, and you may notice that they are not spherical or circular, as normally in phase separation. They are cusp shaped, they are spindle shaped, aligned along the director field, and that's because this is taking place on a pneumatic, so that breaks the breaks the symmetry and gives you an anisotropic line tension. And as time goes by and more lipids absorb the islands, they merge, they grow, and then you see a funny thing here, and that you see an island inside an island. So that's actually an island on the back side forming. So this is a sandwich of islands. And that's because lipid transfers through the shell and starts eventually getting so much lipid on the other side that you get islands forming on both sides, and then you get this trajectory that can be quite spectacular of islands developing on both sides and interacting in very interesting ways. So before telling you why this happens, let me briefly show you what is actually a liquid crystal shell. Well, we make them by injecting water into a liquid crystal phase, and then this compound jet is injected into another water phase, and then they break up by the Rayleigh stability, and you get this shell structure. So this is a cartoon what they look like. They're on the order of, a few microns thick. They are about 100 micron in diameter. And then we're on Earth. We have gravity. And often you have a density mismatch between the liquid crystal and the inner phase. So often the inner droplet sinks to the bottom or rises to the top, which means that the shell will be asymmetric with a thin top and thick bottom, or vice versa. And the stabilizer that we add to the aqueous phase, it's not important only for stabilizing and avoiding collapse, but it's also important for controlling the director configuration. So this is an interesting example where we actually can tune by changing the temperature the alignment from fully tangential, which is on the left, where you see 4 plus 1/2 defects near the thinnest point of the shell, and then as you heat, it goes to hybrid alignment, where you have tangential on one side and normal on the other, or radial on the other, and finally near the clearing point you have radial on the other. This is a movie of what this looks like in very much sped up. And the point is that this is a very continuous transition. So you see the director field gradually changes, the defects move, and you go from tangential to hybrid and eventually to completely normal alignment in the shell. So these shells have been studied by many people for quite some time, using many different stabilizers, polyvinyl alcohol typically for planar alignment, and many surfactants for making normal alignment. What hadn't been investigated is lipids. So we were curious to see how do lipids affect the alignment, and we expected, lipids usually give normal alignment, so we were expecting to see a similar thing if we start with a planar aligned shell. We add lipids in the form of liposome solution, and we thought we would get a similar type of continuous transition. So this is kind of a cartoon of what's happening. We're adding a liposome solution, the liposomes adsorb on the shell, and the lipids spread on the shell. And we saw a very, very different transition. So instead of this continuous motion of the defect, of the director field, we get these coexisting domains of very different configurations, giving rise to a quite spectacular disco ball of beautiful textures. And we were really curious about what's going on and why is this happening. And just to give you an idea what these islands that we see here are, you see in this case we have added liposome to the outside, so the inside is fully tangential, and inside the island you have normal alignment, but outside the island it's still tangential. So we were wondering, because we didn't expect this, we were looking at the literature to see if someone has seen something similar. And indeed, Nick Abbott's group found a similar type of phase separation and these little bit similar looking domains a couple of years back, 2008. This was in flat samples. This is a flat 5CV layer. And they added a liposome solution and found this. So that was clearly useful for us. And this is that paper, a beautiful paper from 2008, where they produced a free energy formula for free energy function for explaining what's going on. And you notice that it has two components. It has the classic Flory-Huggins free energy of mixing, and it had an addition that is unique to the LCs, to the liquid crystals. And that addition it gives rise to this phase separation, even though on an isotropic substrate you wouldn't have that phase separation happening. Now on shells things are a little bit more complicated, and this is an example. So this is what happens when the shells are really thin on top. The previous shell I showed you was fairly similar in thickness everywhere. So islands form everywhere. That's why you get this disco ball texture. But in this case, I'll play the movie once again. This is very much sped up. But you see, there are no islands at the top where it's thin, and all the islands that form, they move downwards. So clearly the asymmetric structure of the shell plays an important role. So in order to model this, well, we have to consider the circular shape, the two interfaces, and the asymmetry. So this is what it looks like in a cartoon, and we call the outside primary and the inside secondary for this time. We don't write inner and outer because we can also reverse the situation. We can produce the shells with the liposomes inside, and then we see everything from in the other direction. So the model has to capture both, and that's why we call them primary and secondary. Because we have this asymmetry, we cannot just integrate over the whole shell. You saw that the events happening at the top are very different from what is further down. But we do have rotational symmetry around the gravity axis. So what we're doing is we're integrating around a conical cross-section, which is indicated here. And what you then have to do is you have to give the radii of the outer shell, uppercase R, and of the inner shell, lowercase r. We have to indicate the offset because of gravity. And we need to write the angle that we call theta that tells where are we on the shell. And as a function of that angle, we have different d, which is the shell thickness that varies as a function of the point location on the shell. And with this, we can now start writing the free energy. So similar to Nick's approach, we take the Flory-Huggins term, but now, of course, we have two interfaces. So the term that Nick used, that's just in this gamma. And you see we have an XP and an XS. For X is the lipid coverage fraction on the primary side and on the secondary side. Then comes the elasticity. Again, we have to consider both the primary and the secondary side. And the alphas here, they are the director angle at the primary and the secondary side. So if alpha is 0, you have normal alignment. If alpha is 90 degrees, you have tangential alignment. And then comes the...
Sorry, you have 2 minutes.
Okay.
Thank you.
Okay, and then comes the anchoring at the in addition. Again, at two interfaces. So we then, because we can't integrate over the whole shell, we compare simply the two tangential and normal as a function of location, and then we plot that first for this shell that was quite uniform, and you can see that you have up to a certain limiting coverage fraction, you have the switch to normal is higher free energy, and then above a critical fraction you get lower free energy, and that's where you get islands. But if you have the more asymmetric shell, which is here, you see then that these are the curves at different points of the shell, different angles. So here you see that further down where the shell is thicker, yes, there is a gain in free energy, reducing free energy, and you form islands, but the top here, you never have a gain in free energy because the elastic deformation is so high at the top. So to summarize, a liposome adsorption on liquid crystal shell leads to quite spectacular phenomena, as you can see also in this video. You get phase separation, you get these spindle-shaped islands with hybrid alignment, you get transfer of lipid from the primary to the secondary side, and when that happens, you have islands on the second side, and they stack together into sandwiches, and then they interact and so on. And there's actually much, much more than I can cover in 10 minutes. For instance, the opposite signs of curvature on the in and the outside play a role, and of course the varying shell thickness and the fact that we don't have any edges on a sphere are very important. So with that, I thank you very much for your attention, and if there are any questions, I'd be more than happy to answer.
Thank you very much. Thanks. This is very, very interesting. Let me see if the audience has some interest. Okay, there is a question here from Cecilia. So fascinating, she said, fascinating work. Do you know for a fact that the liposomes you inject are single layer or smectic multilamellar? Sorry, technical words.
Yeah, thanks, Cecilia. We don't know for a fact. We follow a procedure that where the authors claim that they have checked that it always gives a single unilamellar vesicles. We have done light scattering, and well, the sizes make sense, but no, we haven't really checked that. But we assume that because we're following the procedure.
Very interesting. So apparently you are doing a collab with the laboratory guys, doing experiments and the theoretical people, or how do you detect those shells, and how do you do this framework?
So this is the experiments are done in polarizing microscopy. We make the shells with microfluidics, okay. And then we add the liposomes manually just before looking at the.
Thank you very much. Let me see if there is another. Okay. Yeah, there is. If you can please answer very quickly, there is another question. So are these the same as lipid rafts on water? If you can reply.
Oh, wonderful question. So the big difference is that if you look at lipid raft phase separation in vesicles, the boundaries are always circular. These are cusp shaped, and that's because this happens on a nematic substrate, so that it breaks the line tension. But and this happens on top of a liquid crystal. The lipid raft is really the whole system in itself. But
okay.
Great question.
Yeah, thank you so much. Thank you for this very interesting talk. Please, you can share.
Thank you.
Yourself. So let's move on to the next talk. Will be given by